share this one. Okay, this one. That's the new one. Right. So today I'll be explaining about the subchapter 4.2, specifically about the analysis of functions 2, relative extrema, deriving polynomials. So the first one that we're going to take a look is this one. The relative maxima and minima.
So today I'm going to explain to you what is the first derivative. The first derivative have three graphs. The first one is minimum, the second one is maximum, and the last one is no extrema. So for the minimum, it comes from negative to positive, and for the maximum, it comes from positive to negative, and for the non-extrema, it comes from positive to positive. So the graph doesn't change. So if the graph doesn't change, like positive to positive and negative to negative, it will be a non-extrema graph. For the example is f. So the question is fx equals x squared minus 4x plus 5. So the first thing we need to do is to decrease it. So x squared, we decrease it to 2x, and 4x equals to 4 minus 4, and the 5 equals 0. So the result will be 2x minus 2, and the result of the x is 2. And as you can see, if we try to calculate it manually, if 3 minus 2 the result will be positive. But when we calculate the 1 minus 2, it will be negative. So if you can see, the 2, when when some numbers is so when it so the graph will be the minimum, because it comes from decreasing to increasing, from negative to positive. And to find the result of this function, we need to calculate it by adding the x, and the result will be 1. So the graph will be 2, the x will be 2, and the y will be 1.
We have the second derivative test, which is another way of finding whether a critical point has a relative maxima or relative minima. Sometimes this test is used instead of the first derivative test because it is simpler to use, because by using the second derivative, you can have less variables or maybe less powers to work with. For the second derivative test, if the second derivative at a critical point is greater than 0, then the function has a relative minimum at that point. On the other hand, if it is less than 0, the function has a relative maximum. If it is equal to 0, the test is inconclusive, which means that it could have a relative maximum, relative minimum, or neither. In this case, you may use the first derivative test to get an answer. To do the second derivative test, we need to first find the critical point. To do this, we need to first derive the function. So here f of x equals 2x cubed minus 12x squared. The first derivative will be 6x minus 24x. Then we need to set it to equal to 0. We can then factor that into 6x times x minus 4. Then set each factor to equal to 0 to find the critical point. 6x equals 0 means x would be 0, and x minus 4 means x would be 4. Therefore, the critical points are 0 and 4. Next step is to get the second derivative. After deriving 6x squared minus 24x, we get 12x minus 4. From this, we just plug in the critical points that we got earlier, 0 and 4. So f double prime of 0 will be 12 times 0 minus 24, giving us negative 24. Then f double prime of 4 will be 12 times 4 minus 24, 48 minus 24, giving us 24. Now that we have our values, we just need to evaluate them. We can recall from earlier that when the second derivative is greater than 0, the function has a relative minimum. And when it is less than 0, the function has a relative maximum. So that means f double prime of 0 will give a relative maximum with a graph that is concave down, while f double prime of 4 will give a relative minimum with a graph that is concave up.
Hi, my name is Jacinta Roland, and my student number is 0103424005, and for my part, I'll explain about the geometric implication of multiplicity. So first, let's talk about multiplicity. So in algebraic geometry, the concept of multiplicity is tied to how geometric objects like curves or surfaces intersect or overlap. It refers to how many times a specific point is counted or how many times a geometric condition is satisfied at a particular location. So in simpler terms, multiplicity can describe the number of solutions at a point or how many times an intersection occurs, and how tangent or overlapping geometric objects are at a certain point. So let's suppose that Px is a polynomial with a root of multiplicity m at x equals to r. So A, if m is even, then the graph of y equals to Px is tangent to the x-axis at x equals to r. It does not cross the x-axis at xr and does not have an inflection point there. Right on the screen, it's the example of the graph of roots of even multiplicity. Next. If m is odd and greater than 1, then the graph is tangent to the x-axis at x equals to r, crosses the x-axis there, and also has an inflection point there. So right on the screen, it shows how the graph will appear when the roots of odd multiplicity greater than 1. And the last, if m equals to 1 or so that root is simple, then the graph is not tangent to the x-axis at x equals to r, crosses the x-axis there and may or may not have an inflection point there. Right on the screen is the graph of simple roots. Let's do some example. Consider the polynomial function of x equals to x minus 2 power of 3 times x plus 1 power of 2. Discuss the behavior of the graph of f(x) at each root, specifically focusing on the impact of the multiplicity of each root on the shape of the graph. So for the answer, the root at x equals to 2 has a multiplicity of 3, which means the graph will cross the x-axis at this point, but with a flattening effect, creating a cubic-like behavior. Then while the root at x equals to 1 has a multiplicity of 2, which means the graph will touch the x-axis at this point, but will not cross it, creating a parabolic turning point. So in the screen, it shows how a graph of fx equals to x minus 2 power of 3 times x plus 1 power of 2. Thank you for listening to my part. Next will be explained by Nadia.
Hello, Sir Ferry. Now I will continue to explain about the analysis of polynomials. And as Nadia, I will explain about this. So, first thing first, what is polynomials? Polynomials are mathematically expressions that consist of terms made from variables and constants. So like x, y, other stuff. And they are continuous and differentiable, which means they don't have sharp corners or breaks when graphed. So they always make some slope, like a very melengkung, and it's not sharp like the other graph, like maybe make a triangle sharp graph, other stuff like that. So I'm just gonna go to the understanding degree of graph and shape. So polynomials have a degree. So what is degree? A degree of two polynomial or quadratic can have at most two x-intercept, one externum, maximum or minimum, and no more than one reflection point. So let me draw what does it mean by degree? First thing I also confused what is degree. So degree is look like this. So hard to draw. Here. This one is the degree. The number 2 is the degree. Yes. So, the degree 3 polynomial cubic can have up to 3 intercepts and keep on till 4th degree, which can have 4 x-intercepts, 3 extrema, and 2 inflection 2 points. So I know explaining this is kind of confusing, so I'm just gonna go to the example, the graph example. So this is the example of y equals to x quadratic. The second, no, it's the 2 degree. It is squared, x squared. Now, x squared graph shows an up-facing graph where all are positive. And when it is y equals to minus x squared, it shows a downward graph. So it's like this and like this. So this shows a negative y-axis, and this show the positive y-axis. So let's continue. And here are some the examples on how we act on the infinity, where the x is approaching to what infinity. So if we have this example, positive x squared, if the x goes to the right, then the y goes up. And if the x goes to the left, to the minus infinity, the y is still remain positive because it goes upward, facing upward. And if it's negative x squared, if the x approaching to the positive infinity, the y will approach to the negative infinity because it goes downward. And if the x still goes to the negative infinity, then the y will go downward also to the negative infinity because the graph facing downward, so the y will go like that. So here are the other the last example is when we use 3 degree. 3 degree shows a graph like this. It goes one to the upward and the other goes downward. So if we try to read this as the x approach to negative infinity, then the y-axis will go to negative infinity also, because when it goes to the left, it goes down. as we can see here. And if the x goes to the positive infinity, dy will also goes to the positive infinity, because when the x-axis goes to the right, dy is also goes to upwards. The graph shows an up. So, and for the negative part, it acts the opposite. It reflects the positive one. So, if the x go to the negative infinity, the y will go to positive infinity. And for the reflection, if the no, for not for the reflection. For on the other hand, when the x goes to the positive infinity, the y will go to negative infinity, because when the x goes to the right, the y goes down. So that's how it explains for the polynomials graph.
We're explaining some examples related to our subchapter. Example 1. Use both the first and second derivative tests to show that f of x equals to x cubed minus 3x plus 3 has a relative minimum at x equals to 1 and a relative maximum at x equals to negative 1. To do this question, we first need to prove that the critical points that we need to evaluate is 1 and negative 1. As we know that the maximum and minimum points are stationary points whose gradient is 0, we just need to equate the first derivative with 0. So the first derivative will be 3x squared minus 3, while the second derivative will be 6x. So after we equate the equation with 0, we just solve the equation, and that will give us the result of x equals to 1 and negative 1. Now we need to find the nature of each critical points. To do that, we just need to substitute the critical points that we found before to the second derivative. So when x is equal to 1, the value will be positive or greater than 0, meaning the point when x is equal to 1 is the relative minimum, while when x is equal to negative 1, the value will be negative or less than 0, meaning the point when x is equal to negative 1 is the relative minimum of the function. Find the relative extrema using both first and second derivative tests. F of x is equals to x to the power f of x is equals to x to the power of 4 minus 12x to the power of 3. So same like before, we need to find the first and second derivative. So the first derivative will be 4x cubed minus 36x squared, and the second derivative will be 12x squared minus 72x. And then we equate them with 0 and solve them, and it will give us a result of x equals to 0 and 9. After that, we substitute the critical points of the second derivative, and we found out when x is equal to 0, f of 0 will also be 0, making the point at x equals to 0 an inflection point. While when x is equal to 1, the result is greater than 0. And then, now to find the relative minimum of at that point, which is at f is equal to 9 or x equals to 9, we just need to substitute 9 to the original equation here, which is x to the power 4 minus 12x to the power 3, and we will find out that f has a relative minimum of negative 2186 at x is equal to 9. Now we'll move on to the last example. Use the given derivative to find all critical points of f, and at each critical point determine whether a relative maximum, relative minimum, or neither occurs. First, we need to equate the function with 0. Then to remove the logarithm here, we need to make the argument equal to 1. After that, we can expand and simplify, and we will get 1 and negative 1 as the critical values or points to evaluate. Now, to evaluate the nature of each point, we need to pick a value which is higher and lower than the point that we would like to evaluate. So, for example, if we would like to evaluate the point when x is equals to 1, we substitute x is equals to 2 and x equals to 0 into the function, this function, and we will get a negative and positive result. Now, for these values, we can choose any values, but it's better if it's near the values that we would like to evaluate. Since the derivative of a function is related with the gradient of a curve, we can assume that the negative value equals to negative gradient, which means that the graph is decreasing, while the positive value would mean that the graph is increasing. So here, we will have a decreasing value, positive. Therefore, the negative one will be the relative minimum, and here positive, increasing, and then decreasing, which means that when x is equals to 1, it is the relative maximum of the function. That is all from our group. Thank you for listening.